All right, everybody. I just wanted to go over the conservation of energy lab that's due this week. So let me share my screen. This lab is focused on the principle of conservation of energy. So energy will be conserved if there are no external forces adding energy or removing energy from the system. So the most basic example I can give of this is if you're on a swing set at the park, and if there were no air resistance, if there were no friction in the swing, um, if you started swinging, you would just continue swinging forever and your energy would be conserved. The energy that you have at the top of your path, which is all gravitational potential energy, would be converted to kinetic energy at the bottom of the path, and then that would be converted again to gravitational potential energy at the top of your path. And again, no friction, no air resistance, no friction in the bearings of the swing. You would just keep going the same path forever. Of course, we know that's not what happens in real life. You gradually slow down because there are forces that are removing energy from the system, like air resistance and friction. So your energy is not conserved in that case. But if we can remove friction and air resistance, let's test out what happens, right? So this is the laboratory that you're going to do today. So when you click on the link for the laboratory, you will go here and then click on the one that says measure. This is going to allow you to measure the energies at different points along the path. You want to click stick to track, keep the track a U shape. Initially, we're going to have no friction. And our gravity is the gravity on Earth, 9.8 meters per second squared. And make sure the mass of the skater is 60 kilograms. If you do want to do a different mass, that's fine. Just keep the mass the same throughout the entire lab. You can also check off grid if you would like as well, just to help you see the heights. So let me share the lab document. So the first part is you want to choose a height to release your skater from. Okay, so, and then you're going to calculate the initial gravitational potential energy of the skater at that height. So let me bring up the simulation again. Sorry, I'm bouncing back and forth. Let's put the skater at, I'm just going to say 5. I'm going to put it around 5 meters. Okay, and then release. Notice that because there's no friction, there's no air resistance here, when I release this guy from 5 meters, he reaches maximum velocity at the bottom of the path. He has maximum kinetic energy. And then all of that kinetic energy is then converted back into gravitational potential energy at the top, at the other side. And he always reaches the same height that he started from, which is showing that the energy is conserved. If you start, for example, with 10 joules of energy at the top of your path, you have 10 joules of energy everywhere along the path if energy is conserved. Now that energy changes form, right? As you move along the path, that gravitational potential energy turns into kinetic energy of motion. But the total amount of energy you have is the same throughout the entire path. It just converts forms. So let's say we started him from 5 meters above the ground. I guess it's actually a her, sorry. Let's say we started her from 5 meters above the ground. Let's determine her initial gravitational potential energy. So I'm going to go back to the lab manual. Sorry. And I'm going to type in the initial height of the skater we chose was 5 meters. You can choose a different height if you want. It doesn't have to be 5. The initial gravitational potential energy. Gravitational potential energy, the equation for that is mass times g, 9.8, times the height. So I'm going to do mgh. That's equal to the mass of the skater, which is 60 kilograms, times 9.8 meters per second squared, times the initial height, which was 5 meters. And if I plug that in, I get 2,940 joules. So she starts off with 2, and by the way, energy, the units for energy It's a Newton meter, or another word for that you can use is a joule. So we denote the energy units as joules with a capital J. So she starts out with 2,940 joules of energy. She should have that same amount of energy everywhere along her path. So let's choose another. So question 4 says choose another point on the track and analyze it using the energy sensor tool. Record the final height and final speed at this point and calculate the gravitational potential energy, kinetic energy, and the total energy. Okay, so I'm just going to pause her at a random point. So right here, her height is 1.69. So just take this thing and put it right here. Her height is 1.69 meters above the ground, and she's now moving at a speed of 8.03 meters per second. At this point in space, she has a combination of gravitational potential energy and kinetic energy. There's still a little bit of gravitational potential energy because she's still a little bit above the ground, but she's also moving, so she has kinetic energy. So let's record these 0.69, 8.03 in the thing. She was at 1.69 meters and her speed was 8.03 meters per second. So number 5 says calculate the potential energy and the kinetic energy at this point. So at that point, her gravitational potential energy, mgh, is going to be her mass, 60 kilograms times 9.8, times her height at that point, which was 1.69 now. So now she only has 993.7 joules of gravitational potential energy. Makes sense. She's lost some gravitational potential energy, but she has gained kinetic energy, right? Kinetic energy, the equation for kinetic energy, if you remember from the chapter, is 1/2 m speed squared. So I'm going to calculate that. 1/2 times 60 kilograms times her velocity, which was 8.03 squared. 1,934.4 joules. And so at that point in her path, the total energy that she has is going to be the sum of her gravitational and her kinetic energy. So I'm just going to add these two together to get the total. 2,928. Now notice that it wasn't exactly what we had originally, 2,940 joules. That might be because maybe she wasn't exactly 5 meters above the ground. Maybe I didn't release her at the right spot. But notice they're pretty close, right? And they should be the same, right? In fact, let's go back and actually check what was her initial height. Because maybe I thought it was 5 and it's not actually 5. Let's see. Oh, so her initial height was actually 4.98. So let's see if that changes anything. 2,928. So little tweak, sorry. Let's change that here. Just enough to make it a little bit different. 2,928 joules. Now that matches, right? Our initial energy was 2,928. Our energy at some other point along the path was also 2,928 joules. That's exactly what you should end up getting. It shouldn't change. The type of energy changes, but the total energy does not change. You can do the same process when she gets to the bottom of the ramp. Okay. Again, you should find that her energy at the bottom of the ramp is the same as whatever she started off with. Play around. There's a couple of other questions involving changing the mass of the skater. The question is, does the mass change the velocity of the skater at the bottom of the ramp? You should be able to run the simulation, make a prediction. Does the mass change anything? And then make a prediction about what you think will happen, and then run the simulation with a different mass. If you remember from the last few chapters, if I drop something from an initial height above the ground and there's no air resistance, doesn't matter the mass of the object, right? If I drop a feather and a brick, if there's no air resistance, and they'll both fall at the same rate and hit the ground at the same time. So you should think about that when you're answering this question. Does the mass of the skater affect their speed at the bottom? The last part asks you to add some friction to the skate ramp. So let's see what happens there. We're going to restart. Okay. And let's add medium amount of friction. You can predict that she's going to gradually slow down and stop now because of the frictional effects. So let's observe that. She's gradually slowing down. Eventually, her kinetic energy drops to 0, her potential energy drops to 0. And what you also see here is thermal energy. What's that from? Well, if you rub your hands together, what you're doing is the friction between your hands is creating thermal energy. So all of the energy that she started with at the top, if there's frictional effects, gets converted into thermal energy. Let's see. So she started off with 2,930 joules of thermal energy, of total energy. And at the end, all of that got converted into the thermal energy. So the friction removed energy and converted it into thermal energy. So that's the idea behind that. And then there's a little question at the end, a couple of questions about a roller coaster and a pendulum. You should be able to work through these problems after you have worked through the lab. So I just wanted to go over that with you. I hope that makes sense. Please email me or request a Zoom meeting if you need any help with anything. Thanks a lot. Bye.